Hello, Jake here. Today I'll be talking about droplets covered in insoluble surfactant being driven through porous media under pressure. So if you look over here to the right, these are droplets. They are surrounded by another secondary carrier fluid between the drop and the solid particles. And the whole emulsion is being driven through this porous media. So the porous media is represented by perfect spheres in a periodic lattice. And then the colors on these drops represent the local amount of surfactant at the drop interface. So first I'd like to go over some previous work, specifically by Zinchenko and Davis, who developed a robust computer code to simulate clean drops flowing through a periodic lattice using the boundary integral method. So an important number here is the capillary number, which is the ratio of viscous forces to surface tension. That is shown here. The viscous forces are encapsulated by the gradient of pressure that's being imposed on the system. And a couple interesting properties here. So the drop phase velocity is actually higher than the emulsion phase velocity in this system. That's because these drops are larger than the interparticle constrictions and tend to plug those constrictions and have to be forced through before the majority of the carrier fluid. So that'll become important later, but let's take a look at what that actually looks like. So as you can see, we're on the right, these drops slow down as they're kind of entering these interparticle restrictions and then speed up as they're pushed more toward the center of this periodic cell. So the immediate question is, what will happen if we add surfactants to this system? The main effect of surfactant that will become important here is how it affects the film drainage. So the film is the small intervening layer of fluid between a drop interface and either another drop or in this case a solid surface. So let's say that this is a drop here covered in little surfactant molecules. As it approaches a solid interface, for example, it starts to deform like this, and the intervening fluid needs to flow out from this lubrication layer. So it does that, and in turn it sweeps the surfactant molecules away from the center of this near contact region. Surfactants decrease surface tension. So this gradient of surfactant concentration that's formed also forms a gradient of surface tension. And that in turn gives rise to an additional Marangoni stress. So these Marangoni stresses are essentially trying to return the surfactant to a uniform distribution. So a couple other potentially important effects here. The one is because surfactants decrease surface tension, that locally increases the deformability of the interface. And then, of course, if you have enough surfactant on the surface, you could have total immobilization due to the increasing strength of Marangoni stresses. So we're using just the simple convection diffusion equation, which looks, though, a little bit more complicated because we have this 2D surface kind of evolving arbitrarily in 3D space. Another important point is that we're saying that the diffusion effects are relatively small compared to the convection of the surfactant. So this term here, the diffusion term, can go to 0. So we're using a linear equation of state to relate the amount of surfactant, local amount of concentration of surfactant, to the surface tension. And finally, an important value is the degree of contamination, which we're calling beta, which is essentially a measure of just the total amount of surfactant at the interface. So briefly, here's some more previous results for a single drop embedded in a far-field flow approaching a single constriction. So in this case, the drop flows slower than the carrier fluid and much slower as it becomes lodged in this constriction. And as you can see, it forms what would be a typical trap state if this were a clean drop. However, the surfactant is swept toward this leading tip of this drop, locally increasing the deformability of the interface, and the drop is eventually able to pass through. So the main point here is that it decreases the critical capillary number of the system. So the critical capillary number is the capillary number below which the drop would become trapped in the constriction indefinitely. So in other words, surfactants kind of help the drop to pass through in this case. So let's compare that to this new work with drops in a periodic lattice. So first of all, they're beginning with an initial uniform surfactant coverage at approximately the center of these periodic cells shown on the right here. And they're evolved from there, and they quickly form a regular periodic motion. So we know that, unlike for a single drop in far field flow, these drops are flowing faster than the carrier fluid, and the surfactant is actually swept toward the trailing half of the drop. And actually, we can take a look at what that looks like here. So during several of these stages here, you can see Marangoni stresses are trying to pull the surfactant kind of more toward the first half of the leading tip of the drop, but are unable to completely do so. And for the entirety of this regular periodic squeezing process, the surfactant stays toward the back, and we'll talk about how that affects the overall squeezing. So here's a direct comparison between clean drops completed in previous work and this new system with what we are going to call a low degree of contamination, or a beta value of 0.05. As you can see on the right, this period of motion here is significantly increased with just this small degree of contamination added. And so the question is, why does that happen? The main hypothesis is that the surfactant is just affecting the drainage dynamics, so slowing down the drainage of that thin lubrication layer that has to form every time the drop goes toward the center of the cell and then approaches a new kind of layer of solid particles. Another possible thought is that, so if you imagine a drop which has surfactant on one half of it and no surfactant on the other half, just in a static fluid, when Marangoni stresses make that distribution uniform again, there will actually be the drop will actually be slightly propelled in this static fluid. So it's interesting. So in this case, the surfactant is constantly on one half of the drop and not on the other. So maybe there's some Marangoni propulsion actually happening in this system too, where essentially the drop is trying to swim kind of upstream. So in future work, we'll try to find ways to quantify the relative strength of these two effects. So a very important value is the critical capillary number. As mentioned before, that's the value below which the drop will become trapped indefinitely in the constriction. So as we add surfactant, we actually see that critical capillary number increase in this case. So previous work has shown that the clean drops form critical capillary number of about 0.7. And they also showed that there is a linear relationship between the capillary number and 1 over this t, or the period of motion, to the negative third. And so that relationship still holds in this case, but the critical capillary number does increase. So this is in contrast with, for example, the effective viscosity ratio, which does affect squeezing times, but does not affect the critical capillary number. So we can also look at the effect of increasing the degree of contamination further from what we'll say is low to moderate, or about beta equals 0.05 to beta equals 0.1. So as you can see on the right here, the period of motion does increase again. And another interesting point is that there's a similar maximum surfactant concentration observed in these systems as for the case of a single drop in far field flow. And that corresponds to about a 40% decrease in surface tension. And this is also consistent with experimental observations. So it depends on the interface, but typically the total decrease in surface tension is about no more than 50% of the original value for typical oil-water interfaces. So the next step here is to extend this work to multi-drop, multi-particle simulations. This will come, of course, along with a number of challenges, the big one being how we deal with drop breakup, so how we reassign the concentration of surfactant near this area where the filament thins and ultimately breaks. And another interesting point here is this daughter drop, for example, could have a significantly different density of surfactant than was originally put on the system. So now we have drops breaking apart that have significantly different capillary numbers, and so it's of interest to see how that will affect the overall rheology of the emulsion. So in conclusion, surfactant definitely tends to impede drop motion in this particular system. And by impeding drop motion, we mean that it increases the period of motion and increases the critical capillary number. And this is an inverse trend as compared to single drops in approaching a single constriction in far field flow. We're attributing this to a couple things. First of all, the drop phase velocity in the system is greater than the emulsion phase velocity, so the surfactant is behaving differently. It's swept toward the back of the drop. And therefore, Marangoni effects start to kick in and affect the lubrication layer draining and formation. And then finally, we're looking ahead to We're interested to see how this will affect larger simulations with multiple drops and multiple particles. And I would expect characteristics of both this periodic system and that of the single drop mentioned earlier. Thanks. And of course, reach out if you have any questions or comments or suggestions.